Roughly 5,000 light-years away, behind the backdrop of the Sagittarius constellation, scientists detected an object that emits no light but seems to be racing against time. It all started with observations from NASA's Fermi Gamma Ray Space Telescope, which initially flagged the source as a typical burst of gamma radiation. But something unusual stood out. The signal repeated at precise intervals. This regularity caught the attention of researchers and prompted a deeper investigation. Subsequent analysis revealed that the source was a pulsar, but not just any pulsar. The object was cataloged as PSR J09520607, a name that would soon secure a notable place in astronomical records. This neutron star rotates 707 times per second, squeezing each full rotation into just 1.41 milliseconds. That makes it the second fastest spinning pulsar ever observed. To put that into perspective, helicopter blades on Earth typically rotate about 5 to 10 times per second. This star completes hundreds of full spins in the same amount of time, and it's doing so with virtually no friction or energy loss, sustaining that rotation for millions of years. But to truly grasp this extraordinary performance, we first need to understand what neutron stars actually are. When a star reaches the end of its life, it can go out in a violent explosion known as a supernova. But that explosion doesn't always mean the end. If the star is massive enough, but still below the threshold needed to form a black hole, the remaining core undergoes an extraordinary collapse. What's left behind reaches a density so extreme that even atoms can no longer exist. This is what we call a neutron star. Neutron stars are among the densest forms of matter in the known universe. Inside them, electrons and protons are forced together under immense pressure, merging into neutrons. The result is a stellar remnant made almost entirely of neutrons. Just 1 teaspoon of neutron star material would weigh about 1 billion tons. That means a single spoonful would outweigh the entire mass of Mount Everest. Such incredible density brings with it equally extreme gravity. The escape velocity from a neutron star's surface is nearly half the speed of light. That's why even the path of light bends near these stars. Space and time warp dramatically in their vicinity. The gravitational field is so intense that time itself appears to slow down when viewed from Earth. These effects make neutron stars some of the best natural laboratories for testing Einstein's general theory of relativity. According to that theory, massive objects bend the fabric of space-time, and we experience that curvature as gravity. Under normal conditions, this effect is subtle, but around neutron stars it becomes so extreme that even light's trajectory shifts, and the flow of time itself changes. But what makes neutron stars dangerous isn't just their density. Many of them also rotate at incredible speeds. When this rapid spin combines with the star's powerful magnetic field, the result is a colossal cosmic generator. In fact, some neutron stars possess magnetic fields 1 trillion times stronger than Earth's. This causes the star to emit energy from its magnetic poles in the form of radio waves, X-rays, or even gamma rays. Neutron stars that emit such radiation are called pulsars. They're called pulsars because they send out radio pulses at regular intervals. J0952 fits this definition, but it goes much further. It also emits gamma rays, a feature observed only in the most energetic and extreme pulsars. Gamma rays are the highest energy photons in the electromagnetic spectrum and are typically associated with cosmic explosions or the remnants of supernovae. But this star emits them continuously and with precision, acting both as a cosmic timekeeper and an interstellar warning beacon. The discovery story of J0952 is also remarkable. The star first gained attention in 2017 when NASA's Fermi Gamma Ray Space Telescope detected high-frequency signals coming from its direction. At first, astronomers thought the signals might just be random background noise, but later analysis revealed that the signals repeated at perfectly regular intervals. This was a telltale sign of a pulsar, but clearly not an ordinary one. Initial observations focused not only on the star's rotation speed, but also on the nature of the gamma rays it emitted. Typically, such emissions occur during massive cosmic explosions and are short-lived. But J0952 emits them continuously and with astonishing precision. The pulses are so regular that scientists realize this star could be used like a cosmic timekeeper. Pulsars act like lighthouses in space. With their steady pulses, astronomers use them as a kind of cosmic GPS. And the pulses of J0952 are so precise that they enable measurements even more accurate than those of atomic clocks. This precision is not only vital for space-time measurements, but also plays a critical role in advanced physics research, such as the detection of gravitational waves. But this wasn't the only striking detail. The gamma-ray spectrum emitted by the object revealed signs of intense matter interaction in its vicinity. This meant the star wasn't just spinning, it was also actively pulling in surrounding material, heating it to extreme speeds and releasing high-energy photons in the process. These findings showed that the star wasn't an isolated system. On the contrary, it was interacting dynamically with nearby matter. Following these revelations, both the European Space Agency and NASA's NICER mission added the star to their observation lists. X-ray telescopes revealed a faint but distinct plasma disk surrounding the object. This disk represented matter being drawn in by the star, compressed as it spiraled inward. And that's a rare feature among neutron stars, because most of them are typically isolated, meaning non-interactive. But it didn't take long to realize that J0952 wasn't alone. Radio wave measurements revealed the presence of a companion star in its orbit. This star was a very low-mass white dwarf that had lost nearly all of its energy. Even more strikingly, the companion was shrinking, slowly disappearing over time. This observation offered a crucial clue for understanding the true nature of the system. In the light of these findings, the star's classification in the scientific community shifted. It was no longer seen as just a rapidly spinning pulsar, but also as part of a Black Widow system, a type of star system named after spiders. Just as the female spider consumes the male after mating, these pulsars gradually consume the stars that once accompanied them. J0952, too, was once paired with a normal star. Over time, it began drawing in matter from its surroundings at high speed. As this process unfolded, jets of particles were ejected from its poles and turned into intense radiation storms. The companion star began to evaporate under this barrage of radiation. This process went on for millions of years, eventually driving J0952 into its current extreme state. This cannibalistic behavior placed J0952 in a special category, not just for its spin rate, but also for its mass. Today, it is known not only as one of the fastest, but also as the most massive neutron star ever detected. Mass measurements indicate it has about 2.35 times the mass of the Sun. At first glance, that number might seem ordinary, but in reality, it holds critical significance. In physics, there's a value known as the Tolman-Oppenheimer-Volkoff limit. This defines the maximum mass a neutron star can sustain. Current calculations suggest this limit falls somewhere between 2.5 and 2.7 times the mass of the Sun. J0952's current mass is just below that threshold, meaning the star has reached the greatest possible density before collapsing into a black hole. The star's structural balance lies on a boundary that physicists still don't fully understand. While gravity tries to pull the star inward, its rapid spin generates centrifugal force that delays the collapse. But this delay doesn't imply a stable equilibrium. If the star's mass increases even slightly, say by absorbing just a few billion more tons from surrounding material, that balance could break. And if it does, the star would instantly collapse into a black hole. That's what makes it potentially deadly. Among all the stars ever discovered, J0952 is the one closest to that ultimate limit. In fact, a smaller star with the same mass would have already become a black hole, but J0952 hasn't, at least not yet. And that's exactly why scientists are so fascinated. Why does this star still exist? And how much longer can this fragile balance hold? To answer those questions, J0952 must be compared with other cosmic threats. There are other stars in the Milky Way that pose dangers, some in similar ways, others through entirely different means. Each one is lethal in its own nature, each one a silent menace in space. Roughly 640 light-years away, Betelgeuse is one of the brightest stars in the sky. But that brightness is only temporary. Betelgeuse is a red supergiant nearing the end of its life. It's expected to explode soon as a supernova. When that happens, it will unleash an immense wave of energy spreading across trillions of miles. The resulting light and gamma rays could be powerful enough to reach Earth. Although it's currently at a safe distance, both the timing and direction remain completely uncertain. At about 7,500 light-years away, Eta Carinae presents a more complex and more dangerous system. This binary star contains two massive bodies that are slowly spiraling toward one another. If the merger occurs at the right angle and at the right time, the resulting gamma ray burst could be directed straight at Earth, powerful enough to tear through the atmosphere. Events like these have the potential to wipe out life on a planet, even from intergalactic distances. WR-104 offers yet another scenario. Located around 8,000 light-years away, it stands out with its spiral structure. But what concerns scientists most is the possibility that its rotation axis may be pointed directly at Earth. If this star ends its life in a supernova, the resulting high-energy beam could strike us head-on. While its orientation hasn't been definitively confirmed, the potential for a death ray scenario is closely monitored by the scientific community. A smaller but much more intense threat comes from magnetars. These are rarer than ordinary neutron stars but possess far stronger magnetic fields. They generate magnetic forces trillions of times greater than Earth's. Some of them can unleash short-lived but devastating bursts of energy in the form of X-rays and gamma rays. In 2004, one such magnetar, just 50,000 light-years away, released a blast powerful enough to temporarily disable satellites orbiting Earth. Massive explosions, high-energy beams, magnetic surges, or storms with unpredictable trajectories, each one destructive in its own way. But all of these cosmic threats share one trait: they announce their arrival with warning signs. Changes in brightness, spectral shifts, and preliminary radiation bursts can reveal their presence. And this leads to an obvious question. With so many known threats, why do scientists single out J0952? The answer lies in the unique kind of danger this star represents. The risk isn't just in how close it is to the critical mass limit. The real threat is in how that transformation might occur. Most black holes form through supernova explosions. A star violently erupts and then collapses. This process sends out massive energy and warning signals to its surroundings. But that's not the case with J0952. If a collapse does occur, it will be silent. No explosion, no light, no warning. The star would vanish in an instant. That's because J0952 already began its life after a supernova. There's no leftover energy for a second blast. Instead, the moment of collapse emits no light, no radiation, no detectable signal. The pulsar's steady radio pulses would simply stop. The star would disappear, as if swallowed by space-time itself. This is what sets it apart from other threats in the universe: a quiet, sudden, and traceless death. In short, no one knows when the collapse will happen. It could be tomorrow, 100 years from now, or 1,000, but once it begins, the process will be over in seconds. And the situation is actually even more complex. If the collapse does generate strong gravitational waves or other signals, they wouldn't reach Earth for another 5,000 years, which means the collapse may have already happened and the destructive radiation could be on its way right now, completely unnoticed. That's why, if there's a neutron star capable of collapsing without any warning, every second of its behavior must be monitored. And that is exactly the decision made for J0952. NASA and its network of partner observatories now watch this star 24/7, because what it does next could rewrite not just its own story, but the entire physics of neutron stars. At the center of this monitoring effort is a telescope called NICER. Mounted on the exterior of the International Space Station, this specialized detector was designed specifically to study neutron stars. It records the X-rays emitted by pulsars like J0952 in real time, allowing scientists to detect even the slightest changes in its rotation speed. That's important, because in the moments before a collapse, one of the first things to shift could be subtle irregularities in the star's spin. But NICER isn't alone in this task. Ground-based radio telescopes, the European Space Agency's XMM Newton Observatory, and especially the Fermi Gamma Ray Space Telescope are also involved. Fermi tracks J0952's gamma-ray pulses, measuring the energetic outbursts around the star. Any deviations in these signals can act as early warning signs, potential indicators of a change in the star's mass. Scientists are not only interested in the star as it exists today, they're also deeply focused on what it could become. That's because the structural limits of this star are so sharp and fragile that even the slightest external trigger could push it into a new physical state. This is why observatories, especially NASA, are constantly monitoring its spin rate, tracking the regularity of its gamma-ray pulses, and studying the accumulation of matter around it. But the point here is not just scientific curiosity. Observing this star is also a form of preparation. If J0952 ever collapses, it won't just be a physical event, it will be a test for detectors and scientists across Earth. Capturing such a moment in real time would mark one of the most significant milestones in the history of physics. No one knows when J0952 might collapse. Maybe tomorrow, maybe 1,000 years from now. But one thing is certain. This star exists on the edge of what the universe allows. Watching it isn't just about learning the fate of a single object, it's a way of understanding our place in the galaxy. Because one of the most dangerous stars known to science is quietly watching from deep space, facing Earth. And if it ever goes silent, the missing signal may be far more than just an absence in the sky.